two of the best measurements ever made of the universe disagree by an impossible amount. Not a rounding error. Not a rookie mistake. A gap so wide it should not exist. And after more than a decade of the smartest people alive trying to close it, nobody can. So here's the question. This whole channel keeps circling back to. Why can't scientists agree on how fast the universe is expanding? Start with the thing we do know, because it's worth holding on to. The universe is expanding. That part is not in doubt. Almost a century ago, Edwin Hubble noticed something strange about distant galaxies. They are racing away from us, and the farther away a galaxy sits, the faster it flees. The whole cosmos is stretching, carrying galaxies apart like raisins in rising bread. That relationship between distance and speed has a number attached to it. We call it the Hubble constant, and it is basically the speedometer of the universe. Measure it well, and you can do something almost unreasonable. You can run the entire expansion backward to the moment of the Big Bang, or forward to whatever ending is waiting for us in the deep future, one number. The age of everything, and its fate, riding on it. So you'd want to measure it carefully. And we have. There are two great ways to read that speedometer, and the whole problem, the entire reason this video exists, is that they don't agree. The first way looks deep into the past. About 380,000 years after the Big Bang, the universe finally cooled enough for light to travel freely for the first time. Before that, it was an opaque fog of hot plasma. After that, the fog cleared, and the light released in that instant has been traveling ever since. It is still arriving today, stretched out by all those billions of years of expansion, as a faint glow filling the entire sky. We call it the cosmic microwave background. It is, quite literally, the oldest light there is, a baby photo of the universe. And the Planck satellite mapped it in breathtaking detail. Every tiny ripple and temperature variation across the whole sky. From that baby picture, plus our standard model of how the cosmos works, you can calculate how fast the universe should be expanding today. You don't measure it directly. You predict it. And the answer comes out to about 67 kilometers per second per megaparsec. Hold on to that number. 67. And here's what makes it serious. This is not one lonely result from one instrument. The DESI survey, mapping the positions of millions upon millions of galaxies and reading a subtle ruler baked into them called baryon acoustic oscillations, lands in the very same neighborhood, somewhere around 67 to 68, two completely independent windows onto the early universe, and both of them whisper the same low number. Now the second way. This one ignores the deep past entirely and just measures the universe sitting right in front of us. It's called the cosmic distance ladder. And it is exactly what it sounds like. A series of rungs, where each rung calibrates the next, climbing from our own cosmic backyard all the way out to galaxies hundreds of millions of light years away. You can't measure those enormous distances in one step. So you build them up, carefully, one trusted rung at a time. The lower rungs lean on a special kind of star called a Cepheid variable. These stars are remarkable. They pulse, they swell and shrink, brightening and dimming on a steady, clockwork rhythm. And here is the gift, hidden in that rhythm. The speed of the pulse tells you the star's true brightness. So you time the pulse. You learn how bright the star really is. You compare that to how bright it merely looks from Earth, and the difference gives you the distance. The JWST team, led by the astronomer Adam Rees, used hundreds of these Cepheids to calibrate the next rung up the ladder. That next rung is the Type 1a supernova. These are exploding stars, and they have an almost magical property. They all detonate at very nearly the same intrinsic brightness, every single time. That makes them perfect cosmic mile markers, brilliant enough to be seen clear across the universe. So you anchor the supernovae with the Cepheids. You let the supernovae carry you out to the most distant galaxies, and you read off the expansion. Stack the whole ladder together, rung by rung, and the local universe gives you an expansion rate of about 73. So there it is. The early universe says 67. The nearby universe says 73. And at first glance you might just shrug. Measurements have error bars. Things in science rarely line up perfectly. A few points apart, who cares? But that is exactly the part that should stop you cold, because both teams know their own uncertainties down to fractions of a percent. They have squeezed the error bars smaller and smaller for years, and the two answers still flatly refuse to overlap. The gap is not shrinking. The better the measurements get, the more stubborn it becomes. Let's put a real size on the disagreement. It now sits at about 5.4 sigma. In plain language, sigma is just a way of measuring how unlikely a fluke is, and 5.4 sigma means the odds of this gap being a random statistical accident are roughly 1 in a million. Think about that. In physics, the gold standard, the line you have to cross before you're allowed to claim you discovered something brand new, is 5 sigma. We have crossed it, but not to announce a new particle or a new force. We crossed it to announce something stranger. That two of our most trusted, most carefully built measurements of our own universe simply do not match each other. Scientists gave this stubborn gap a name. They call it the Hubble tension. For years, the comforting bet, the thing most people quietly assumed, was that someone had simply made a mistake. And the prime suspect was the distance ladder, because it has the most moving parts. Maybe the Cepheids were contaminated. Maybe dust between the stars was dimming them and throwing off the brightness. Or maybe, in crowded galaxies, neighboring stars were blending into the Cepheids, faking extra light and corrupting the measurement. If you could just find that hidden error, the tension would melt away. The two numbers would slide together, and the universe would make comfortable sense again. So, the hunt was on for the flaw. And then the James Webb Space Telescope arrived, with vision sharp enough to finally settle the argument. This was the instrument everyone had been waiting for. Webb could resolve those crowded Cepheids cleanly, splitting each star apart from its neighbors, seeing exactly the kind of systematic error everyone suspected was lurking in the old data. This, surely, was the moment the tension would quietly die. It didn't. When the dust settled, and sometimes that's almost literal, Webb's measurements landed right on top of the older Hubble results. They matched. The crowding explanation, the leading suspect, was rejected at 8 sigma confidence. 8. Even more decisive than the tension itself. Instead of erasing the local number, Webb confirmed it. The 73 held firm. The easy way out had just been slammed shut and bolted from the other side. The tension didn't ease. It got harder, and the mystery got deeper. So, if it isn't a mistake, what on earth is it? Here is where we have to leave solid ground and step carefully into theory. The most exciting possibility and I want to be honest that it is only a possibility, is that the tension is completely real. That it is the universe itself telling us our standard model is incomplete. That somewhere in the long stretch between that ancient light and the galaxies in our neighborhood, something is happening that our equations simply do not capture. A missing ingredient. The leading candidate even has a name. Early dark energy. The idea goes like this. For one brief chapter in the infant universe, long before any stars, a hidden burst of dark energy switched on, did its work, and then faded away. That little early push would shrink a key cosmic ruler used in the early universe calculation, and shrinking that ruler would nudge the predicted expansion rate upward, away from 67 and towards 73, finally closing the gap. It is elegant. It's the kind of idea physicists fall in love with. But it is also unproven. And every time we test it against fresh data, it only half fits. It patches one problem and tugs at another. Nobody has made it work cleanly, and honesty demands one more complication, because this story is not as tidy as headlines make it sound. Not every local method gives you 73. A separate, respected team, using a completely different kind of star, the tip of the red giant branch, measures a value closer to 70, right in the middle, sitting awkwardly between the two camps. So the truth is, the field cannot even fully agree on how big the local number really is. The tension is solid. It is real. But its exact size and shape are still being argued over in papers right now, and that's not a weakness in science. That is science refusing to lie to itself, refusing to round away an inconvenience just to feel finished. Which brings us to right now, to this very year. The Euclid Space Telescope is out there, mapping the shapes of billions of galaxies stretched across 10 billion years of cosmic history, and its first major cosmology results, expected later this year, will hand us a third, fully independent check on the expansion of the universe. A fresh pair of eyes on the oldest argument in modern astronomy? It might confirm the tension. It might deepen it. It might even point at last toward the fix. But as of today, right now, it has resolved nothing. The question is still wide open, and the field is holding its breath. So here is the honest answer to the question we started with. Scientists can't agree on how fast the universe is expanding because, as far as anyone can tell, both answers appear to be right, and they cannot both be right. The early universe and the nearby universe are handing us two different speedometer readings for the same cosmos. The gap has survived every single attempt to explain it away, and the most precise telescopes humanity has ever built keep making the problem sharper, not softer. We may be staring directly at a crack in our understanding of the universe, and a crack, in science, is not a failure. It is exactly where the next great discovery gets in. Nobody knows yet which way this breaks, and there is something quietly, genuinely thrilling about being alive in the exact moment right before we find out. If you like the cosmos told straight, what we actually know, what we only suspect, and what nobody knows yet, then subscribe. This channel publishes The Honest Cosmos every single week. One question before you go. If these two measurements never reconcile, would you rather it turn out to be a hidden mistake we can finally fix, or brand new physics that rewrites the rulebook entirely? Tell me in the comments.